Welcome everyone to the Aerodynamics Podcast. This one is about 7 techniques for becoming a better aerodynamicist. My name is Mike and we'll be going through these. I also got a new lapel mic, as you can see. Yeah, just for you guys. All right, so the first technique for becoming a better aerodynamicist is you need to learn the basics better. Now, this is something that a lot of people don't want to do. And the reason why is because research in general, when you're doing aerodynamics, not just aerodynamics, but research in general, we always want to skip to the most complex stuff. The problem is that if you don't understand the basics, you can never understand the complex stuff properly. And you see it all the time where, people will be saying stuff that's quite complex, and then everyone else will be nodding along, and then you don't understand it. So you ask the person next to you, like, hey, what's going on here? And they don't know. They just nodded along because they don't want to seem stupid. But the basics are the key to everything. If you don't understand the basics properly, then you cannot understand the complex stuff and you won't be as good at aerodynamics. And let's give you some examples. So, for example, the Reynolds number. Everyone knows that the Reynolds number is the density times by the velocity times by the characteristic length divided by the viscosity. And we all know that. So we use Reynolds number in almost everything. We can tell sort of what a flow is doing when the Reynolds number is, let's say, 100,000. Sometimes you go into more detail and then we explore more. So we think, okay, well, what is the Reynolds number really? And you look at the top line and you realize that these are the inertial forces. And then on the bottom line, they're the viscous forces, the viscosity. So if you look at the equation, it's the ratio of the inertial forces to the viscous forces. And so we go into the basics a little bit more there and we think, okay, great, we understand it a bit better now. So we know that if the Reynolds number is quite high, it means that the inertial forces must be dominating because that's the much larger term. But then there are additional things that you need to know about the Reynolds number. For example, if you have a flow, the quintessential example is over an airfoil. But lots of other objects follow this similar sort of path, which is as the Reynolds number increases, the lift and drag coefficient change. But that doesn't mean that when you have Reynolds number 100,000, the lift and drag coefficient is always going to be those values. And the reason why is because it also depends a lot on what the turbulence intensity is. The reason why the Reynolds number is so important is because it gives an indication as to how turbulent or well behaved the flow is. But that is also dependent on the turbulence intensity, what's happening upstream, how is the free stream flow reacting? Is it aligned even? So all these things also impact how the wing or whatever object you're testing performs. So it's not just the Reynolds number, but if you were to look at, if you were to dig into the basics, you just go, okay, the Reynolds number is 100,000. Now we know that's this, and then you keep moving on. But that's not the case. Another example of where you need to dig into the basics is, for example, the dynamic pressure. So I've written down an equation here. You should be able to, let's see if I can read it. Yeah, so this is the dynamic pressure equals half times the density times by the velocity squared. We all know that. That's one of the things that you first learn, although a lot of people don't actually understand it and forget it. But so this is an important equation, and we use it for a lot of things. We use it to determine what the velocity of the wind tunnel is, unless you're using the other method, which is where you have 2 points that you've correlated to the wind tunnel speed, and then you can read off whatever graph you have. But most of the time, we use this equation to determine what the velocity of the wind tunnel is. We also use it to non-dimensionalize the drag and lift, so you get the lift and drag coefficients as well as moment coefficients and side force coefficients. But what is it really? So I'm going to hold it up again, and so you can see it there. What equation does this remind you of? Dynamic. Here you go. So you can see it better that way, I think. Dynamic pressure equals half times density times by the velocity. This equation looks very familiar. It's very similar to another equation that you learn very early on in science. So I want you to pause the video and just have a think about it. What does this look like? Okay, I assume that you've paused the video. You probably haven't, because when someone says that on a video, I don't do it either. But anyway, let's say you have paused the video. I'm going to write down another equation that looks quite similar. Okay, so on the bottom line here, you have EK, kinetic energy, equals half times the mass times by the velocity squared. Now these two equations look almost identical. There's only one difference, and that's the density instead of the mass. But the density equals the mass divided by the volume. So in reality, these two equations are very similar. They're only separated by the volume. So what does that mean? It means that if you know what the dynamic pressure of a certain amount of air is, and you know how much air you have, you know how much kinetic energy it has. And that makes sense because the dynamic pressure only exists when there's flow moving. When the flow is not moving, there is no dynamic pressure, there's no velocity. So that gives you zero. So that shows you that the dynamic pressure and the kinetic energy are effectively, they're not the exact same thing, but they're very closely related. And they effectively show the same thing. You just need to multiply by the volume to get the kinetic energy of the flow. So once you understand that, okay, so when the flow is moving very quickly and if the density is high, you get a lot more kinetic energy. And that's where all this pressure comes from when you have flow hitting a wall or a stagnation point and decelerating. That energy just creates that pressure. So learning the basics is really important. We just went through a couple basics there, and I'm willing to bet that what I just told you about here with the dynamic pressure and the kinetic energy, you've never heard before. The reason why is because I'd never heard about it. I never heard any lecturer, any researcher ever say anything about it. Never read it in any textbook. No one even whispered it. Yet it's quite, once you see it, it's quite obvious, and it's quite important for your thinking to understand what's going on in the flow. So learn the basics better. The second technique to becoming a better aerodynamicist, this is to be okay with looking stupid. And this is a very difficult one for most people to do. And the reason why is because as we progress in aerodynamics, when you first start doing aerodynamics and aerodynamics research, you don't want to look stupid because you think, oh, are they going to kick me out of here? I better look smart. They try to help them think that they picked me for a reason. And then it doesn't get any better. Like when you start doing more and more aerodynamics, you go through a master's, PhD, whatever, and you become a researcher, and you're doing aerodynamics for 10, 20 years, you still have that feeling because now you've progressed and you're thinking, well, I can't look more stupid than that person because I'm more senior. Now, the thing is that everyone is stupid. No one knows everything about aerodynamics. Most people don't understand even 1% of aerodynamics. So you should get used to looking stupid. And the reason why is because you cannot learn something that you think you already know. And if you pretend to know something, you can't learn that because you can't then break it down and examine it because of the fear that someone else is going to see you doing that and you're not stupid. So you should get used to looking stupid. That's the only way that you can progress. If you don't look stupid, it means that you're not progressing, you're not pushing yourself hard enough. And the thing is, the more you look stupid, the more you progress. That really goes hand in hand. Now, the third technique for becoming better at aerodynamics is to ask questions and don't stop. And this sort of feeds into the first two techniques as well, where you need to learn the basics better, and you also need to be okay with looking stupid. Now, asking questions is fundamental to learning. And again, I've been in conferences and everything where the speaker says something and no one dares to ask a question because they don't want to look stupid. They don't want everyone to think that, oh, I don't know something that everyone else knows. But the fact of the matter is, we all learn different things at different times. So when you first start out, for example, when I first started out, I didn't know much about boundary layer flows. I knew the basics, not that well either, so I had to research that more and more. But then if I went to a conference where there were a lot of boundary layer people there, I would look stupid and I need to ask questions to understand. But if those people then came to a conference on my topic, which was airfoils at the time, they would look stupid because they don't understand nearly as much as what everyone else there understands about airfoils. And so they need to ask questions to learn. And if you don't ask questions, then you can't learn either. So that's the third technique. The fourth technique is be open to the strengths and weaknesses of different approaches. And this is a very important technique. I'll get a quick drink first. Now, the reason why this is really a very fundamental thing that everyone needs to do, and in a lot of ways, a lot of fields in aerodynamics need to grow up. And that is because in aerodynamics, there's this there's a lot of competition, and not just in aerodynamics, but research in general. But in aerodynamics, for example, you have CFD people versus aerodynamicists, versus experimentalists in aerodynamics. Then you have theoretical aerodynamicists versus experimentalists. And then you have even like boundary layer people versus, let's say airfoil people. And then you have like in the aircraft people, it's like, or what's the most important part of an aircraft? You have people who work on wings, they say it's the wings because they produce lift. Then if people working on the power plant, they say, no, what's the power plant? Because without the power plant, you're not going anywhere. And then it's like with avionics, well, if you don't have avionics, then you can't get off the ground either. So it's like, what's most important? And there's a lot of competition going on. The fact of the matter is that they all work together. And by falling into this idea of which one's better and only being staunchly in this category or that category, you miss out being able to use all of them together and play where one has weaknesses, you use the strengths of another approach or field to complement that and make up for that. And a great example is CFD and experiments. So as I said, CFD and experiments, they are people doing these are often very staunchly against each other. But the fact of the matter is that they complement each other. Everyone knows that you can't get that much information from experiments compared to CFD. Like CFD you understand everything about the field. But then on the flip side, you don't know if the CFD that you're doing is right, and you need experiments to validate it. Most of the time. Sometimes you can get away with not having that much validation if it's a very simple case, and theoretically and all this sort of stuff. But anyway, so you have these strengths and weaknesses, and then with CFD, you then can sometimes get carried away where you say, I want to make the CFD really accurate, and then it's like, well, CFD produces this effect. It's very easy to just fall into CFD where the time just gets sucked up, where you just keep putting more and more time into it to make it better and better. You change the mesh theory, you change the mesh state, you refine it, you change the boundary layer, you change the solvent properties, you change the relaxation, you change how much you're running the steady state initialization for, and then how much you're running the transient state, and then what the time step is, and you can change everything. And it's so easy to just get sucked into it. And before you know it, like days have passed, weeks have passed, and you're still playing around with all these little settings to make it better. So that's where understanding what you need to achieve with it helps. And that's often done by understanding how it works with everything else that you're doing. So if you're using experiments, for example, if you're only using experiments for validation of the CFD, then go ahead and make the CFD better. But if you're using CFD just to complement the experiments a little bit, just to look at certain features better, you don't need to make CFD that much better. So you need to understand the strengths and weaknesses of them. And then furthermore, you don't have just CFD and experiments in aerodynamics. You have panel methods, you have other numerical things. So panel methods with viscous coupled solvers, you have lifting line theory, and then you have empirical data, you have theoretical data. All of these different approaches can work together. One of the major benefits of panel methods, which I really like, and lifting line theory, is even though they're not very complex, they're incredibly quick. Like you can run, in the time it takes to run one good CFD simulation, you can run like 200 panel methods easy. So you can get a lot more understanding about what the flow is doing, and with different parameters. So if I change, like for example, this object, if I change its geometry a little bit, how does that affect the flow? You get a general idea. Of course, you're missing out on the accuracy that CFD provides, but you have a very quick methodology to get a better understanding, and then you can use that to complement your CFD development perhaps. So be open to the strengths and weaknesses of different approaches, and don't be closed off just to one approach. They all need to work together. The fifth technique for becoming a better aerodynamicist is to read widely. And this is, again, a very important topic that I just covered before, where, if you're an airfoil aerodynamicist and you go into a boundary layer presentation, you often don't know much about it. And that's because the experts in this field, And you're not an expert in that because you're only reading about airfoils. So you need to read, and the thing is that boundary layer flows are very important. So if you don't understand boundary layer flows, then that can hinder what you're doing in your experiments or your CFD or whatever you're doing, because that really, and CFD is actually a very good example, because CFD you need to understand what the different thermospoiling is doing. So that's very important to understand, that you need to read widely, not just your topic, and don't get pigeonholed into just one topic, but to read all these different topics, and not just in aerodynamics. You don't need to just limit yourself to aerodynamics. For example, really, no matter what research you do these days, including aerodynamics, computer science is incredibly important. Like, everyone needs to know how to code these days. The better you know how to code, the quicker you're going to be able to achieve what you want to achieve, and more accurately. So you need to read up on comp sci. And you can even look at biology, for example. There are many times where, when I've been doing aerodynamics, I've looked at biology and, for example, evolution patterns, and seen how different aerodynamics have formed, and what ideas that's given me for my stuff to develop. And it's really helped a lot. And that isn't something that's normal. Most people in aerodynamics are not going to read evolutionary papers or biology papers to get ideas on what to do. But you'd be amazed at how many profound ideas you can get from there, and really accelerate what you're doing and your field. So the next technique for becoming a better aerodynamicist is, it sounds cheesy, but it's very important, and that's to love aerodynamics. And the reason why that's the case is because everything I've talked to date, it involves a lot of work and a lot of learning, and also, for example, being okay with being stupid and asking questions and all that. If you don't love aerodynamics, then you're not going to be okay with making those making that happen, because you're going to be wondering, I don't want to look stupid. So, but if you love aerodynamics, you don't care what anyone thinks, you just want to do it, and that's really going to supercharge how much you're learning. So you need to be okay with what we said before, and that's achieved through loving aerodynamics. And the final technique, the seventh technique for becoming a better aerodynamicist, is to be curious. And what do I mean by this? So it happens all the time where you get a job at, let's say you're in a research group, or you're in consultancy or whatever, and you get there and you learn their ways, and that's great. For example, CFD, this is a very common example. Let's say you get a job as a consultant in an aerodynamics company, and you're doing CFD with some other people, and these people, they have their regular methods on how to process the data. And this is all true. Like, for example, if you get an consultancy, you'll be getting often get these codes that you just run on your CFD results, and they'll pop out all the data that they want to see. So, for example, you might get all these different planes at certain distances downstream. You might get certain coefficients and isosurfaces or whatever. Now, that's great, because that means you have all this data that you can compare to what everyone else is doing, and you're doing it in a standardized way. But by only relying on that way of processing your data, you're not looking at everything else that could be there. And when these people developed their codes to process the data, that might have been great for those objects. But when you look at other objects, there might be other little bits in the flow that you want to look at, or maybe you understand something different about aerodynamics that they don't. And so you might want to look in a certain area to find some clues as to how to improve your aerodynamics, or what to look for. And then, but they don't know that, and these codes don't look into that area. So you need to look into that area and look at different methods. So you need to be curious and play around with things. So, and that's really the best way of producing work efficiently. It sounds very counterintuitive, because you think like, well, if I'm playing around, I don't know what I'm going to find. But that's the thing, you don't know what you're going to find. And often you're going to find things that are very profound. If you just keep on relying on these codes, you're never going to find those things. And if for every research campaign that you do, you spend even half an hour or an hour just playing around with the data afterwards, just to see what you can find, you're going to find a lot of things that you wouldn't have found otherwise and that are important. And with experimental campaigns, the thing of not just experimental, but CFD as well, experiments to some extent, a bit more. These are very long campaigns. So, the setup takes weeks, probably months even. CFDs are the same with trying to get a good mesh setup can take a very long time. Carrying it out will take days, sometimes weeks. So then you look at the data processing, and if you don't process the data adequately, then you're missing out on all this information that you should be getting, and it's becoming inefficient. What you've just done throughout this entire period, you might have 6 months worth of work, and you're only getting out 20% of what you could be getting that would help you. So that's very inefficient. By squeezing out every little bit of data that you can get, you then maximize all that work that you just put in. It's data processing is like getting to the end of a race and then just falling over the finish line. You're not finishing it strong. You need to finish that last little bit. So those are the 7 techniques for becoming a better aerodynamicist. They are: 1, learn the basics better. 2, be okay with looking stupid. 3, ask questions and don't stop. 4, be open to the strengths and weaknesses of different approaches. 5, read widely, even different topics, not just aerodynamics topics, but topics in general about other things. 6, love aerodynamics. And 7, be curious. If you want to become a better aerodynamicist, check out the courses that we offer at Premier Aerodynamics. The link is in the description. You can get there by premieraerodynamics/courses. And make sure to check out some of the instruments that we produce. And that's all I've got for you this time. Peace out.